Hello and good morning, grade 9 with you, Mr. Samir Awad. As we did before, chapter 4, and we start by defining the atom. Today we are going to start second lesson, which is structure of the nuclear atom. Now we will start by part 1 of it. So, from its name, the nuclear atom, we are talking about here about the subatomic particles or the structure of the atom from inside. We talked about the size, we talked about the models for the scientists about the atom, but now we are going to start to get more involved inside. First of all, how did scientists determine the structure that are inside the atom? It's like the doctor when he's going to scan your bones if you get broken or something like that. So he has to start to you know, expose you to X-ray. And that's what we are going to do today. We are going to expose the atom from inside to know the structure of it. And that will be the beginning. First of all, we have something is called subatomic particles. That means that we are going to divide the atom into parts inside. And that's the opposite of Dalton's and Democrats. Let's see. Yeah. So much of Dalton's atomic theory is accepted today. One important change, however, is that atoms are now known and be divisible. That's the difference today. And they can be broken down into smaller fundamental particles called subatomic particles. And the three subatomic particles we have to know about it, it's electrons, protons, and neutrons. First of all, the electrons and how they discovered the electron. And all of the honor got to Mr. J.J. Thomson, who was the English physicist in 1897. He started to get his experiments in order to know more about the electrons. And he defined the electrons as are negatively charged subatomic particles. Thomson performed experiments involving passing electric current through gases at low pressure. He sealed the gases in gas tube fitted at both ends with metal discs called electrodes, and the electrodes were connected to a source of electricity. Like we'll see that is called discharge or electric discharge tube, and evacuated from any air except for the gas which is inside through the vacuum pump. You will get here the two electrodes here, the one, the negative one, and the other one is the positive one. And here it's called the high voltage batteries giving the current to the tube. And here we'll get guys that the negative electrode is called the cathode and the positive one is called anode. And we will get that what happened. Notice that when he start to connect the battery to the electrodes and the gas with low pressure is inside, a beam of electrons start to move there, or beam is called the cathode ray. He got it like a ray here, and the rays is starting from the negative cathode to the positive anode. And that means that there's something attracting this ray to go from there to there. So the cathode ray that traveled from the cathode to the anode here, we got it. And Thomson found that the cathode ray reflected by electrically charged metal plates. So when he got to get electrically charged metal plate in the beginning, he got it deflected here. Yeah. When the positive is getting there, it will attract to the positive plate. And when it is coming to be negative plate, it will start to rebel and go away from it. So that's like repulsion with the negative and attraction to the positive. That give indication to Thomson in order to know that there will be a charge on this ray and the charge of it will be negatively. So he hypothesized that cathode ray is a stream of tiny negatively charged particles moving at high speed. And Thomson called this particle corpuscle, or by the end, he named it as electrons for easier definition. And the electrons here will get the cathode ray and also deflected by magnet. So it can be affected by the magnet and by the negative and positive charge, even by attraction to the positive or diffraction, or as we said, repulsion from the negative one. And to test his hypothesis, Thomson set up an experiment to measure the ratio of an electron charge to its mass. And he found this ratio is be constant every single time he makes this experiment. Also, the charge to mass ratio of electrons can depend on the kind of the gas or even the metal in the electrode. And that's give him indication that the electrons are similar, are identical for each element. Yeah. So there's no difference between the electrons inside the hydrogen and the electrons inside the oxygen, except for the number. In the structure, they are the same. In the charge, they are the same, and in the mass too. So Thomson concludes that electrons are a component of the atoms of all elements. And after that, we get a new scientist to start to prove more about this thing. And he was USA physicist Robert A. Millikan. He started to carry the same experiment of Mr. Thomson, but he started to use, instead of the gas, he used negatively charged oil droplets. So he put between the two droplets, it's charged plates. He then changed the voltage on the blades to see how this affected the droplets rate of fall. And that gives him indication that they start to be charged by a charge multiple of 1.6 times 10 to its power negative 19 coulomb, and that's meaning that will be the same charge of the electron. Also, using this charge, Thomson get from the charge to mass ratio that made by Thomson the calculations of the electron's mass. And that was to get the new value for it. It was accepted up till today. So he said that the electron has 1 unit of negative charge. That's what we get. And its mass is 1 over 1,840 the mass of hydrogen atoms, which is the smallest atom in the periodic table. So that's also giving us that the electron's mass is very, very, very tiny. Let's go further to protons and neutrons. And if cathode ray are electrons given off by atoms, what remains of the atom that have lost the electrons? For example, after hydrogen atom, the lightest kind of atom in the world, will lose an electron, what is left after that? So you can think through this problem using 4 simple ideas or principles we know about the matter and the electric charge of it. Number 1, atoms have no net electric charge. They are electrically neutral. There is no charge. The positive charge is equal to the negative one. So overall charge will be always 0 for the atom. And electric charges are carried by particles of matter. Electric charges also always exist in a whole number multiple of single basic unit. That is, there are no fraction of a charge. I cannot say I have half electron or I have 0.75 electrons. No, it will be integer numbers, 1, 2, 3, or 0 electrons even. So when a given number of negatively charged particles combines with equal number of positively charged particles, the electrical, there will be electrical neutralization for the particle here because the positive is equal to the negative. So it follows that the particle with 1 unit of positive charge should remain when it typical hydrogen atom loses an electron. And in 1886, Eugene Goldstein started to know more about the cathode ray tube, and he found when he noticed that some rays are not going in the same direction from the negative cathode to the positive anode, but some of them are going back to the cathode in the opposite direction, and that gives him a conclusion that there will be positively charged particles or subatomic particles going back. They are called protons. And on this time and after that, they start to new another type of subatomic particles, which is neutrons, coming by Mr. James Chadwick, and confirmed the existence of yet another subatomic particle called the neutrons. And the neutrons are subatomic particles with no charges, but with mass nearly equal to the mass of proton. And here, guys, we'll see that we have a table giving us all of the information about the subatomic particles. We have electrons, we have protons, we have neutrons. The symbol for electron is E, it's with negative here, exponential here we'll get, and proton is P, and positive charge will be, and neutron will be small, and it will be zero of it. There is no charge for it. The relative charge here for the electron is -1, for the proton is +1. So if you have one electron and one proton in the atom, like in the hydrogen, it will be neutrally charged and the overall charge for it will be 0. And also we'll have neutrons inside the atoms, and the neutrons charge is equal to 0. There's no charge for it, but it has mass. And if you get to the relative mass and mass of proton, will equal to 1, and relative to this mass, we'll get that the mass of electron will be 1 over 1,840 of the mass of proton, and the proton will be 1, and the neutron will be 1. That's relative mass. But when I get to the actual one, the mass of electron is 9.11 times 10 to the power -28, and that's too small. Also, the protons will be 1.67 times 10 to the power -24, and same for the neutron. That's too small for subatomic particles. Although protons and neutrons are extremely small, theoretical physicists believe that they are composed of also yet smaller subnuclear particles called quarks. And that's very, very tiny and small. So let's get some, refreshing. What evidence did Thomson have that lead him to conclude that if a ray was a stream of tiny negatively charged particles? Yeah, exactly. The ray was attracted to a metal plate with positive electric charge, and Thomson knew that opposite charges attract and like charges repel or start to diffract from each other. Thank you for listening, guys. Next time we'll get to start the second part of our session. Mr. Samir Awad, be safe at home, and good luck, guys. Bye-bye.